All right, this time I'm going to go ahead and get started. Again, I ask you guys if you haven't done so already, go ahead and chat me your first and last name. Uh, I did offer a session at the beginning to ask questions, but does anybody else have any questions they'd like to ask before we get started? All right, well, we're going to go ahead and start working then. And last time we had started doing quite a bit in chapter five, but we didn't quite get finished. There was some more examples I did. You can look at what I posted today. So, for instance, my PHY 241 D01B met at 12:30 today online, and because of that, I recorded that meeting and I solved some of the problems that we didn't get to for your class last time. So I highly recommend you look at least at the examples there. The very first example I do is one of the homework problems that one of the students asked me. That's worthwhile to see. Then I do one for just a mass being spun around over their head at a small angle, meaning the rope's not perfectly horizontal. It's at a slight angle, but we assumed it was horizontal. I worked that one. Then I worked one in a vertical circle, slightly different from the one in the textbook. So that's available. That means I'm going to start off right now with the conical pendulum. So that's what problem I'm going to start with here. Ooh, well, I thought I was going to, but now I see where I moved my name file is not helpful. Oh, there it is. Uh, Anyways, all your names are across the top, and they're preventing me from seeing the pages that I need to see. There's another student came in. All right, now I've got all that satisfied, and that means I just need to go to this will be this will be example 513, and it says conical pendulum, a small ball of mass m suspended by a cord of length L revolves in a horizontal circle of radius r equals L sine theta, excuse me, where theta is the angle the string makes with the vertical. A, in what direction is the acceleration of the ball? And B, what causes the acceleration? Or excuse me, that's not and B. And what causes the acceleration? And then B is calculate the speed and period time required for one revolution of the ball in terms of L, theta, G, and omega. So that's the problem we're going to attempt to solve first. It's example 513. All of a sudden, my pen just stopped writing. Uh, as we said, it has a mass m. It spins with a tilt in the axes of angle theta. So what we're seeing is a string that's attached to a sealant, say. It makes an angle theta. And then in addition to that, on the end of the string, and the string, of course, has a length L. So that's that length there. This bob has a mass M, and of course, it has a weight associated with it as well. So I'm going to try to go ahead and make the free body diagram right there on the picture. So I'm going to call this the x-axis. I'm going to call this the y-axis. And the forces we have acting on this object are going to be the tension force, which is also at that angle theta, obviously. But that's the tension T, and I made it neither green nor red because it hasn't been broken down into components that are perpendicular or parallel to the x-axis. So that's not very helpful yet. But we do have the fact that the weight, which is given by m times g, that is parallel to the y-axis. Now, since this angle right here is theta, then that means this angle right here is also theta. And the reason why that's the case is because this string sort of looks like a piece of 2x4 or rebar laying across two railroad tracks. Specifically, uh, you could imagine the x-axis as one railroad track and the ceiling as another railroad track, and then you'd see that alternate interior angles are equal. But in this case, the alternate interior angles would be this angle right here and then this angle right here. But the main part of that is 90 degrees of that is not relevant. So if we subtracted 90 from both of those, we'd still get theta for what was left. So that's how that worked out. Now I need to make the tension. I need to break it up into components that are parallel to the x-axis and parallel to the y-axis. So this one right here is T, and then that would be times cosine theta. That's the x comp or the y component, and also pointing in the positive direction is T sine theta. So if I take my summation of the forces in the y direction equals mass times acceleration in the y direction, we're imagining this bob spinning around in circles. And why is it not showing? That's weird. All right, we're imagining this bob spinning around in a circle like this, and that means the height is not really changing at all. So we have our normal scenario where I can set the summation of the forces in the y direction equal to 0. In this case, I get T cosine theta minus mg is equal to 0. And that allows us some equation, but we don't necessarily know what's helpful right now, so I'm just going to label that 1 and see what comes out of it. Now I'm going to do the summation of the forces in the x direction equals mass times acceleration in the x direction. This time the acceleration is in the x direction, and it's actually the centripetal acceleration. That was part of the question they're asking. So when an object is making a turn, say, then the turn is supposed to accelerate towards the center of that curve. So our curve is a circle that's horizontal like this, and therefore the centripetal acceleration must also be horizontal and towards the center of the circle. So I often will put that by just drawing an acceleration vector somewhere, and that's what I'm doing right here. I just drew it there. I don't want to put it on the force diagram or the free body diagram because then it would be confused as a force, and acceleration is not a force. You can't add it to forces and all sorts of stuff like that. So that'd be a problem. I don't know why my image stopped showing. Do y'all see my face still? Because I make some occasional gestures with my hand, and I don't see my own image up here, so I'm afraid that y'all won't see it either if I'm making that. Can y'all see me anymore? Yeah, okay, cool. As long as you can, I don't care. All right, so the summation of forces in the x direction, what we see is the only force acting in the x direction, and therefore the force that's supplying our centripetal acceleration, has to be the horizontal component of the tension. So with that, I get T, well, I was writing in blue, so I should probably continue doing that. I get T sine theta is equal to, in this case, mv squared over r. And they specifically gave us an R. I look back at the problem right now. It says R is equal to L sine theta, and you can obviously see that as well. I will indicate it right here. That distance is R, which equals L sine theta. So down here, I'm going to put L sine theta in blue, like that. And that's going to be equation 2. So this is another case where it's probably convenient to do a trick like for solving the system of equations that you wouldn't have seen in math class. So I'm going to divide equation 2 by 1. So divide 2 by 1. So I've got T sine theta over, and by the way, I'm going to make 1 into T cosine theta equals mg. So that's the version of 1 I'm using right now. So when I divide it, it's going to become T cosine theta on the left-hand side. And then on the right-hand side, I've got the right-hand side of 2, which is mv squared over L sine theta, but also have divided by mg. So all of that's going to be multiplied by mg down here at the bottom. And you can see from that that the m's are going to cancel out. Not only that, you see that the t's cancel out. So now what we have is tangent theta, because sine over cosine is tangent. So tangent theta is equal to v squared over L or G times L times the sine of theta, like that. So that's what we have for it. If we wanted to, we could go ahead and solve for the velocity, because what they asked in this question, if I reread it, it says a small ball of mass m suspended by a cord of length L revolves in a horizontal circle of radius r equals L sine theta, where theta is the angle the string makes with the vertical. A, in what direction is the acceleration of the ball, and what causes the acceleration? So the direction, as I pointed out, was actually horizontal towards the center of the circle. And what causes the acceleration is the force t sine theta. So I answered all that. And then part B, they want us to calculate the speed and period of the ball in terms of L, theta, G, and M. So if I were to go ahead and try to, solve for velocity, I have an expression with just velocity, g, L, sine theta, and technically m is included, but m disappeared, so it doesn't depend on m. With that being said, I can say that v is equal to the square root of g times L times sine theta times tangent theta, like that, and that's pretty much it. So that is one way you could actually write it. Of course, there's other ways you could use, various trig identities and simplify stuff like that. But this is sufficient. What we could do, for instance, is v is equal to, I could break the tangent back up into sine over cosine, and then it'd be the square root of g times L times sine squared theta over cosine theta, like that. And of course, you could also reduce that to the square root of GL over the square root of cosine theta, all of that times the sine of theta. So all of those are reasonable expressions for the answer to part B. And like I said, the answer to part A was this little box where A is horizontal, and this t sine theta is the cause of the centripetal acceleration. Now we can set V, because the other part they wanted to know was the period. We can set V equals 2 pi times L sine theta, because that's what R is. So 2 pi R over the period is equal to V, but we know V is in fact equal to the square root of GL over cosine theta times the sine of theta. So if we want to go about solving for t, we can take the t to the top, and then we're going to get equals 2 pi L sine theta times the square root of cosine theta. All of that, of course, will be divided by the square root of g times L. And then, of course, the sine theta will be on the bottom. I could have canceled out that sine theta before when it was sine theta on each side of the equation, but it doesn't matter too terribly much. We could also keep the 2 pi, which generally we like in our formulas for the period. Oops. So if I choose to do that, I get t is equal to 2 pi times the square root. Now, what I'm going to do is I'm going to force that L to become L squared, and then I can force it under the square root. So I'll get L squared cosine theta, because that was already under the square root, divided by g times L. And then, of course, the sine is in the bottom too, but that's not in the square root, so I'll leave that for right now. And I'll just say 1 over sine theta. Not the best looking thing, but it's okay. I'm still playing with it. Now that I pulled that L squared in there, that exponent of 2 can cancel out and just leave a L in the top and a G in the bottom. And I can go ahead and force the sine under the square root by making it equal to by squaring it. So in this case, I get 2 pi times the square root of L cosine theta over G sine squared theta, and I believe that's it. And 2 pi L sine theta. Yeah, that looks equivalent to the form they have, or equivalent to one of the forms they have. So that's it. Remember, when you're talking about circular motion, if it's uniform circular motion, that means the velocity is constant, and therefore the velocity will always be the circumference of the circle divided by the period. So that's 2 pi r over the period. Anybody have any questions on that? All right. So, like I said, there's probably some other ways you could do that, but that's a pretty neat one. Anybody have any questions?
As a refresher, with the sine squared, cosine squared, like any of those, when it's squared theta,
Hmm.
how do you type that into the calculator?
When I'm looking for the square of the sine or the square root,
Yeah, so like in that last one, it's like it's 2 pi, and then there's that at the bottom, the g times sine squared theta. Like, do you
right?
type in your angle and then you do squared after
Yeah.
that?
What I do is I normally put parentheses around the trig function
Okay.
and go ahead and write sine of theta, and then at the end of the parenthesis that's around that sine theta, I put the caret key and then put a 2 for squaring, and that
Okay.
way I like
Okay.
to do
I
it.
just wanted to make sure that I was like
Yeah,
conceptually doing
you'd
that
like
right.
to have a way to actually force it to be there in the middle like we do when we write it, but
Right,
there's no such
right.
thing in a
Like,
calculator.
yeah, that's where I was like, oh, okay. Thank you.
No, I get you. I understand. Anybody else? All right. Well, let's go to a banked curve. Last time I actually worked a flat curve. This time I'm going to work a banked curve, and I'm specifically going to use the example that the book has, which is or more one more or less like it, and that's example 515. So, example 515 says, for a car traveling with a speed v around a curve of radius r, and actually they use a lowercase r. I'm going to use an uppercase r because that looks like something different to me instead of just a coordinate. So for a car traveling with speed v around a curve of radius r, determine a formula for the angle at which a road should be banked so that no friction is required. I don't know why I'm reading a's with so much force, but that's what I'm doing. So first off, we're supposed to calculate the angle theta at which the curve should be banked so that I don't need any friction. To do that, of course, I'm going to assume that the velocity is v. I'm going to assume that the radius is r. And I will need a mass to put in the equation. So I'm going to assume the mass is m, but they didn't give us that. So that means we're supposed to pretend like we don't know it. So what we'll do is we work with the m as if we do know it and then hope that it'll actually cancel out somewhere in the algebra. If it does, then yeah, you were right. You could solve it without the mass. But if it doesn't, then either you made a mistake and it was supposed to cancel out and you could solve it, or you didn't make a mistake and in fact you have to have the mass to solve it. But that's what we're doing here. I do know the mass will disappear in this case. Now in part B, they want to know what is theta if V equals 50 kilometers per hour and R is 50 meters. Notice I went ahead and made everything 3 sig figs for that, but that should do us. So now I need to draw the coordinate system and then I need to draw the free body diagram. This is what I warned you about on virtually all inclined plane type problems we work. We always tilt our coordinate system to be parallel, have our x-axis say parallel to the incline, and then the y-axis would be perpendicular to that. In the case of calculating the banking of a curve, we do not tilt the coordinate system. So again, that's just a reminder to let you know, do not tilt the coordinate system. So I'm going to go ahead and draw a coordinate system like that. And now I'm going to draw a axis that goes up like that. This is going to be our y-axis. This is going to be our x-axis. And really, it's a car, but again, we're treating it like a point object. We'll say it has a mass m, and we'll hope that that mass m never pops in to bite us. But that's what we're going to call it. Now, in addition to this, we have that the actual road that it's sitting on should be an inclined plane. So I'm going to draw it right through here like this, and that's going to be our inclined plane. And from that, we can make the conclusion that this angle right here is theta. Because of that, you can imagine that little dash line as one of the railroad tracks and the x-axis as another railroad track, which makes this angle right here also theta. Now, in addition to that, we're going to have a normal force that doesn't align with the x-axis or the y-axis. It just happens to be perpendicular to the blue inclined plane. So that's the actual normal force that the car experiences. So I'm just going to call that the normal force N. I don't know if I can't even remember if I've been calling this F sub N or just plain N. I'm going to call it N. Okay. And because this angle is theta that I just showed you, you know that this angle to this angle is 90 degrees. So this one must be 90 minus theta. But this angle to this angle is also 90 degrees. So this one must be 90 minus 90 minus theta, which you can see is just plain theta. So we now have, in addition to that, the angle theta here. Now, we also have acting on this the weight of the vehicle that acts straight downward, and that is W equals M times G. We also are going to have the normal force broken up into components parallel to the y-axis and parallel to the x-axis. So this right here is in cosine theta, and this one right here is in sine theta. Now we're trying to design this curve with no friction, so we don't have any additional forces that are acting on it. We just need to go about solving our Newton's second law. So Newton's second law says the summation of the forces in the y direction equals mass times acceleration in the y direction. Again, we're imagining this car going around a circular banked curve, but staying at the same elevation. So the y should not change at all, which means the acceleration in the y direction is going to be zero. From this, we get the force acting upward is in cosine theta. The force acting downward is mg, and that's all equal to zero. So what we can get is that the normal force is actually equal to mg over cosine theta, and I'm going to call that equation 1. Now I'm going to take the summation of forces in the x direction, let that equal to mass times acceleration in the x direction. That's the only acceleration we'll be dealing with, so I'm not going to subscript it x anymore. But I will remind everybody that in fact there is a acceleration going in the positive direction. In order for this to maintain a circle, the acceleration has to be a equal to ac, and I'm imagining the center of the circle is off in the positive x direction. So the car is coming out of the page, but it's also turning to our right. Now, with that, we can go ahead and do the summation of forces in the x direction. You'll notice without friction, we only have that component of the normal force that's parallel to the x-axis. So that's what's actually causing the vehicle to accelerate towards the center of the circle, which it has to do in order to maintain a circle. So with that in mind, our F equals ma becomes n times the sine of theta is equal to m times v squared over r. Again, I'm using the big R, whereas your book used the small r. Okay, that's equation two. Now, we don't necessarily want the normal force, so we don't necessarily have to deal with that, but we do have a way of getting rid of it because I can take equation one and plug it in two, and that's what I'm going to do. Plug one into two. When you do that, I'm going to get mg times the sine of theta, because the sine was already there, over the cosine of theta, because the n is actually mg over cosine theta. All of that is equal to mv squared over r, and this is where you see that the two masses do in fact cancel out. Not only that, we recognize that sine theta over cosine theta is actually equal to tangent theta. So I can go ahead and say that theta is equal to the inverse tangent of v squared over g times r. Now, that is the formula, and that's the right formula, but your book and your author is going to ask you questions that seem completely unrelated. Like it'll say, what must be the banking angle for an aircraft that's making a turn of such and such a radius at such and such a speed? Well, if you take the time to work out the force diagram for that, the free body diagram for that, you'll find out that the exact same equation applies. So that's me giving you a little hint that you can use that anyways. Now, another student coming in. So now we have that, and that's part A. Now all I want to do is solve part B, which is working on a specific curve to find out what the angle would be. So in that case, theta is equal to the inverse tangent of v squared over GR. Now, V is actually supposed to be 50 kilometers per hour, but that turns out to be, if you convert it, remember 50 kilometers per hour can be multiplied, or I should say divided by 1 meter per second per 3.6 kilometers per hour. That allows the kilometers per hour to cancel out, and it should give us 13.888 meters per second. Now, I did have three sig figs because I forced it to be that in the 50. So this should come out to three sig figs as well, which means the second and third eight are not sig figs. But either way, we're going to go ahead and put that in there, 13.888 meters per second. That quantity is going to be squared, and then I'm going to divide it by 9.80 meters per second every second, and times 50, which is the R, which is 50.0 meters, and I'll make that a square bracket so it looks a little more tame. So this is going to be the tangent inverse of, if I work out these quantities, I'm going to square that 13.8. Now that's 192.901. Now I'm going to divide that by parentheses 9.8 times 50, close parentheses, and that gives me the inverse tangent of 0.39368. So I carried more than the required number of sig figs, and now I take the inverse tangent of that, and that gives me 21.488 degrees is equal to theta. And that's our answer. So if you want a vehicle to make a 50 kilometer per hour turn, that's 50 meters in radius, and you don't want friction to be required, then you need to make sure the angle is about 21 degrees. Now, the danger of that, of course, is if you actually go too slow and you're literally on a sheet of ice, then you're going to slide down the incline towards the center of the circle, which if you've ever looked at exit ramps, you notice sometimes they have ponds down there and little cliff edges and all sorts of stuff like that. So it is something to keep your mind on. So, anybody have any questions before we go on to the next part? Now you'll look, there are some videos in the module for this week, and I moved a couple of them that I didn't get to cover last week. Well, I should say, I moved a couple of the videos from last week's module, and I'm going to move them into this week's module, just because we're still touching on chapter five. So you'll see that there. But one of them is me calculating a banking angle if we assume that we do have friction. So that's a slightly more difficult problem, but you can watch that on my YouTube channel. Anybody have any questions before I move on to the next thing? Okay. So the next thing they're talking about is non-uniform circular motion. So in principle, when an object is going around a circle, okay, the object might be right here, say, and it might have a velocity this way. But when you have that, you can have an entirely different acceleration. You have, for instance, to have a circular path like that, you have to have a component of acceleration that is radial. And we call that particular acceleration A sub R for radial. But if you're also going in this circle, you can imagine driving in a perfect circle in a really open parking lot with, no cars around or whatever. If you went at a constant speed, then the only acceleration you'd have would be this radial acceleration, and that's the centripetal one that gives you v squared over r. But if you were to hit the brake or to hit the gas, you're going to discover that there's another acceleration as well. If you hit the accelerator, for instance, the other acceleration would be parallel to the velocity, and it would be like drawn here. If you hit the brake, of course, it'd be drawn backwards, but this acceleration is called a tangent. So this is the tangent acceleration. Now you can see these two are automatically at right angles to each other. So when you add two vectors tail to tail, the result is completing a parallelogram and then draw a vector from the common tail to the diametrically opposed corner. And this is the A total that we're getting right here. And you might even say that this angle right here is phi. And we could say, for instance, that the tangent of phi is equal to opposite over adjacent. So the opposite would actually be AR, and the adjacent would be A tan. And that would actually allow you to figure out what that angle is. So this is something that's useful for you to have. And additionally, you could find the magnitude of that by anybody want to guess how we find the magnitude of A given that it has a component A tan and another component A sub R? Anyone? It's every bit as simple as you might be thinking.
Is it just adding them together?
Yes, you add these, actually, you add the square of them because it's a Pythagorean thing. I don't know if that's what you said. I couldn't hear you that well, but it's A tangent squared plus A radial squared. Notice those words I'm using, tangential and radial. Okay, but that's how you find the magnitude of an acceleration. All right. The A tangent, by the way, is also considered to be dv dt. But you'll notice that part of that, uh, when I derived the AC equals v squared over r, and I got you guys to do it, that was found from dv over dt. So that's not the best way to just think about it, because the dv dt could also give you the AC, but that's often how we think about it. The other thing I want to remind you is the radial part is almost always v squared over r, like that. And we should be able to solve problems like this. So with that in mind, let's work on example 516. So example 516 says two components of acceleration. A race car starts from rest and accelerates at a uniform speed of 35 meters per second in 11 seconds, moving on a circular track of radius 250 meters. Assuming constant tangential acceleration, find A, the tangential acceleration, and B, the radial acceleration at the instant when the speed is v equals 15 meters per second. So it says a car starts from rest, so that means v0 is equal to 0, and it finishes at, it says race car starts from rest and accelerates at a uniform rate to a speed of 35 meters per second. So that's vf is equal to 35 meters per second, and it does so in t equals 11 seconds. Moving on a circular track, and that radius of that circular track is 250 meters. Looks like 2 sig figs is the rule for the day. Assuming constant tangential acceleration, find A, the tangential acceleration. So A tan equals question mark. And B, they want us to find the radial acceleration, AR equals question mark, when the instant at the instant the speed is v equals 15 meters per second. Okay, so first off, let's calculate the acceleration. We know, for instance, that A is equal to delta V over delta T, and that's the average, but they said uniform rate accelerates at a uniform rate. So in this case, we say that it's a constant. And that's going to come in handy. And in fact, all we have to do is say A is equal to V final minus V initial over the time taken. The V final we already have is 35 meters per second. The V initial is 0 meters per second, and the time is 11 seconds. So we're dividing 35 by 11. That gives me 3.18. 2 meters per second. And we only had 2 sig figs, so I'm going to underscore the 8 and the 2 to keep track of that. So that's our actual acceleration, and that happens to be A tangential. So A tan is equal to 3.1, well, we might as well round it to 3.2 meters per second per second. And that was what we were asked to find, so we found that. Now for part B, they want us to find the radial acceleration. So for part B, what we're going to do is B, we have A radial is equal to V squared over R, but specifically we asked for it at 15 meters per second. So that's going to be 15 meters per second squared, which gives us 225. And then I'm going to divide that by 250 meters. So 15 squared is 225 divided by 250 gives me 0.9, and that's meters per second is equal to a radial. And again, that is at 15 meters per second. Anybody have any questions on that? Now, just for the purposes of being complete, I'm going to go ahead and show you that A total is equal to the square root of 3.182 meters per second squared plus 0.900 meters per second. I should say per second r squared. I think I said both last time. So apologize for that. 3.182 squared. Now I only have two sig figs there, and that basically gave me 10.125. So the 3.182, when I square that, that only allows me the two digits that are whole numbers. Now I got to see what zero point 0.9 does. Zero point 0.9 squared, of course, is going to be 0.81, and that means I only get the first and second decimal place for that one. But when I add those two, they're actually going to not align at all. So I'm doing a little bit of cheating, but I'm basically saying 0.81 plus 10.125124 was the result I got. That gives me the square root of 10.935124 meters squared per second to the fourth. Now, technically, we were only good in the whole numbers places, so all of these are not sig figs. But now I can take the square root of this number by raising it to the 0.5 power, and I get A total is equal to 3.307 meters per second is equal to A total. And additionally, I might want to find out what the angle is. So what we found was the radial one was zero point 0.9. So I'll make that kind of small and I'll draw it this way. 0.90 meters per second. And then the other one was kind of big. It was 3.2 something another. So this is 3.182 meters per second. So completing the parallelogram, we get the final vector. A total is this one. And that A total deviates from the velocity by an angle phi right there. And that angle phi is given by, or phi, is given by the tangent inverse of 0.900 over 3.182. So I'll take shift tangent inverse parentheses zero point 0.9 divided by 3.182, and that gives me 15.79 degrees, but neither one of those are sig figs. So I'm just going to say that's equal to phi. And now we have a little bit better understanding of what the whole acceleration vector is. Anybody have any questions on that? All right. Now that we have that, I'm going to do. We've got plenty of time actually, so things are looking pretty good here. I'm going to go ahead and do velocity dependent drag forces. So it turns out there's a couple of different scenarios in which we can write. Uh, why did I say Navier-Stokes earlier? Earlier, I called this equation the Navier-Stokes equation. I want to say that Navier is part of it, but I might be thinking of Poiseuille, Poussoile, Poussoile or something. But anyways, there's a law that tells us from fluid mechanics what the drag force is. Now, the drag force is almost always either proportional to the velocity or proportional to the velocity squared. We don't necessarily care too much about what the coefficient or what the actual constant is that makes FD turn into or what makes the velocity turn into FD when we multiply it by B. So our two choices are drag forces. One of them is F drag is equal to a magnitude, I should say, is equal to B times V, and the other one is F drag magnitude is equal to uh, let's call it B prime times V squared because I don't want to introduce a new constant, but I'll tell you that B depends on what fluid slash gas the object is flying through. And it's not necessarily flying, it could be just running or whatever. And it also depends on the cross-sectional area. Oops. And what I mean by cross-sectional area is whenever an object is moving, if you imagined the outline of the person. So imagine like Wile E. Coyote or Roadrunner, how they run through walls in cartoons or Bugs Bunny or whoever. They leave an outline of their body. Well, that outline is really the cross-sectional area, or at least the area of that outline inside of it. So if you imagined that it takes a certain amount of paint to cover a square foot, and you calculated the number of square feet in that hole that Wile E. Coyote left in the wall or door or whatever, then the cross-sectional area would be related to the number of gallons of paint that you had to put on that to cover that space. So the cross-sectional area has to be perpendicular to the velocity, but that's the main thing. And it also depends, like I said, on the viscosity. You can sort of think that that's somewhat related to density, but really viscosity is the more important point. Uh, for instance, it would take much more work to run through an atmosphere made of syrup than it would through an atmosphere made of air. Okay, so that's how that works. We're only going to study the first case, which is this one. Okay, and to do that, I'm going to let you guys imagine an object in free fall, and then we're going to change it up a little bit. So I'm going to call this my y-axis, and I'm saying the y-axis is pointing downward. This is a mass M, and the force acting on it is in fact just the weight. Remember, if we're talking about free fall, an object in free fall, then the only force acting on the object is the gravitational force, which is the weight, and therefore M times G. That's what free fall is. But we're trying to study what happens like when you actually have some air resistance or air drag or air drag force acting on it. So I'm going to add another force, and in this case, it's going to be F drag is equal to B times V. Okay, and you can see by the way I've drawn my coordinate system that we're going to treat W, the direction of the weight, as the positive direction, and we're going to treat the direction of the drag force as a negative direction. But what you should be able to notice, and I've mentioned this before, is that as this object that's falling gets faster and faster, then the drag force B times V gets bigger and bigger. Eventually, what's going to happen is the drag force is going to get so big that it cancels out the weight. And when that happens, cancels out weight. When that happens, you have BV is equal to mg, and the velocity in that case is what we call the terminal velocity, and it's mg over b. Now, I'm going to show that as well by doing the actual calculus part, but the main thing is I wanted you to understand physically that all that's happening here is b times v is equaling mg, and therefore it doesn't have any ability to accelerate anymore, and that's why they call it the terminal velocity. So if I write Newton's second law in the y direction, then when I do it this way, I'm going to write it instead, because this is a case where the acceleration is not a constant, whereas most of the problems we've been working so far were the acceleration being a constant. But when the acceleration is not a constant, then you have to use a is equal to dv dt, or even d2x over dt squared. In this case, I'm just trying to solve for the velocity as a function of time, so I only need the m dv dt. So using that, what I have is mg minus bv is equal to m dv dt. What I'm going to do is multiply both sides by 1 over mg, and that's going to give me 1 minus b over mg times v is equal to 1 over g times dv over dt. Now I'm going to multiply both sides by g dt, so that's going to give me g dt on the left. And when I do that on the right, I'm also multiplying by 1 over 1 minus b over mgv. So this is going to become dv over, oops, this is going to become dv over 1 minus b over mg times v. So that's what we call a separable differential equation. I was able to get the dv on one side, and the only variable that's with it is the variable v, and the dt doesn't have any variable with it. So as long as you don't have any variable with it, you're good to go. So to solve this, I'm going to integrate both sides, and you could do it as an indefinite integral, but you can also do it as a definite integral, and that's what I'm going to do. So g dt is the left-hand side, and we're integrating with the variable t, so I'm going to take this from t equals 0 to just plain t, and then on the right-hand side, we're going to get the integral of dv over 1 minus b over mg times v. And this is going to be from v equals 0 to v of t. I'm just trying to be pedantic and showing you that we're going to get the velocity as a function of time as one of our outputs. But before we do that, we need to do a substitution. We're going to say let u equal 1 minus b over mg times v, then du is going to be equal to negative b over mg dv, which also means dv is equal to negative mg over b times du, which I think is the easier way to use it. So now I can say the left-hand side, I'm going to go ahead and integrate that because that's just a constant. So the left-hand side is just going to become g times t. Remember, that's g times t evaluated at t equal t minus g times t evaluated at t equals 0. That gives us 0, so we don't have to do any more than what we've done here. Now on the right-hand side, we're going to get the integral. I'm going to leave the limits of integration off. We're just going to substitute in the u, and then once we plug it back in, we'll put the limits of integration back on. So what we have now is a negative because of the change of variables. We found that the dv is equivalent to negative mg over b times du. That's what dv is. And then all of this, of course, is divided by u. And we know that the integral of du over u is just the ln of u. So this is going to give us gt equals negative mg over b times the ln. Now I'm going to do the ln of what u was, and what u was 1 minus b over mg times v, and we have to evaluate that from v equals 0 to v of t. So now I've got gt equals negative mg over b times the natural log of 1 minus b over mg times v of t minus the ln of 1. And of course, remember, this is a expression that will come in handy over and over again. Y equals log base b of x doubly implies that x is equal to b to the y power. So when I look at ln 1, what I know is that I'm actually asking what power do I raise e to get 1, and that is clearly 0. So the ln of 1 is 0, and now we have gt equals negative mg over b times the natural log of 1 minus b over mg times v of t, like that. Now, we can go ahead and multiply both sides by negative b over mg. So I'm going to multiply this side by negative b over mg. And then, of course, if I do that to one side, I've got to do it to the other. And what we're going to get now is that negative, notice the g is going to cancel out, negative b over mt is all that's left on the right hand side, and that's going to be equal to the natural log of 1 minus b over mg times v of t. I'll put that in the square bracket. Now what I'm going to do is imagine raising e to the left side power and then raising e to the right side power, setting them equal to each other. When I do that, remember, if you raise e to the ln power, then the result is just the argument of whatever you have in ln. So in this case, I'm going to say e to the negative b over m times t is equal to just 1 minus b over mg times v of t. Working with that a little bit more, we can see that we'd have v of t times b over mg is equal to 1 minus e to the negative b over m times t, like that. Now I'm going to multiply both sides by mg over b. And that's going to give us v of t is equal to mg over b times 1 minus e to the negative b over m times t. And that's our velocity as a function of time. You'll look at it, it looks like it's asymptotically approaching something, and it really is. If you want to find the terminal velocity, then v terminal equals the limit as t approaches infinity of v of t. So if you look at V of t, which is mg over b times 1 minus e to the negative b over mt, if you take the limit as t approaches 0, the exponential is going to go to 0, and therefore you're just going to get mg over b, and that's exactly what we expected the terminal velocity to be, mg over b. Anybody have any questions on that? All right. So I think that's a good sample of examples from the textbook in chapter five. We're finished with chapter five. I'm going to go on since we've got 20 minutes. I'm going to go on into chapter six. I did push the due date on chapter five, though I thought I did it Friday or Thursday, but I found out the day it was still set to the 22nd. I've now pushed that back to Sunday. Which is March 1st. So your due date on that has been extended, so that should help you a little bit. That being said, we also have a face-to-face, or excuse me, an online test that's due on 3/1. So I made the practice test available to that for that today, and the actual online test will be popping up probably tomorrow or the next day. But let me get started on chapter six. So, chapter six is called Gravitation and Newton's Synthesis. So, chapter six, Gravitation and Newton's Synthesis. Okay, so if you read his Principia, which was written in Latin, by the way, I have a copy of it here on my desk, but it's quite a tome because when you buy one, you not only get the Principia, which is long, but you get the Principia in Latin and the Principia in translation, so you literally get two versions of it. But what he argued was that while sitting under a tree in his mother's apple orchard, his mother literally owned an apple orchard, and that's sort of how she made a little money. She was not wealthy. He didn't know who his father was. Evidently, she got pregnant, and the father left. And then she proceeded to more or less. And I don't want to use this word, but I sort of do because it's funny. But he basically pimps him out. So what happens is he's got an uncle that obviously is related to the mother, and he comes over to check on her on occasion and check on Newton. And what he's discovered is Newton's a very bright person, so he starts bringing him books from the college and that sort of stuff. His uncle is actually a pretty big figure in the church and has access to a lot of things, and he's also kind of wealthy, at least wealthier than the mother. He says to her, "Hey, Newton's really bright. You know, I'm bringing him these math books, and I thought he was just faking it, but like he's working out proofs and all this stuff, and I think he really should go to Cambridge." And she says, "Well, I just can't afford to send him to Cambridge." He said, "No, no, no. I mean, I'm going to pay for him to go to Cambridge. You won't have to pay anything." So this is where she proceeds to, as I told you, pimp him out. She says, "Well, I couldn't stand to not have him here. I need him to, run our farm and that sort of stuff." So instead of the guy being able to pay Newton's way and, maybe even give him some help so he can pay room and board and all that good stuff, he has to pay Mama a little bit for the right to send her son to college. So it's kind of a bum deal. That made Newton kind of bummed because Newton had to actually clean the chamber pots of the wealthier kids. So, they didn't have running water back then. They literally had a canister next to their bed where they relieve themselves in the night, and then Newton's job would be come in the morning and clean out all those chamber pots. So you can imagine that wasn't very good. And in fact, Newton ended up becoming a very hostile, angry young man who had a list of some, 500 enemies and stuff like that. In fact, when we finally translated his uh, commonplace book, which is like a book that you just carry around, and when you're a scientist in that era, you're constantly on the lookout for people trying to steal your stuff. So you normally write your book in such a way that no one can read it. So you make up a script or you make up some kind of language, and then you write it in that language. And that's what Newton had did. And we found that book, but we couldn't find the translation for the commonplace book. So ultimately we finally did, and when they found it, everybody's like super excited because we're like, here's Newton, this holier than thou guy who's, spent his whole life like bragging, literally bragging that he was, 70 some years old and a virgin. And he was, he literally wrote over 500,000 words on the Bible, where he was trying to read the Bible in Greek, the New Testament specifically in Greek, and hoping that he would find sort of the elixir of life or the fountain of youth, some way to live forever. He was looking for numbers inside the script and all sorts of crazy stuff like that. But he put a lot of work into that. So everybody was very excited to hear, how pristine and godly was this Newton character. So they look through it, and after they translate it, and they see, 1,000 entries like, "Forgive me, Lord, for today was the Lord's day, and I got angry," or "Forgive me, Lord, for today was the Lord's day, and I ended up doing some work that needed to be done instead of resting like you're supposed to," and just a bunch of really boring stuff like that. And then all of a sudden they write us one passage, and it says, "Forgive me, Lord, for today I wish the death of 50 people." So he's not necessarily a happy guy. But that being said, I highly recommend you read a biography of him at some point. The chapter 6 starts off with Newton's universal law of gravitation, and what I was saying was Newton had seen an apple while sitting under an apple tree in his mother's orchard, and he looked up and he saw an apple hanging from the tree, and then in the distance he saw the moon. And he figured out at that moment what the moon and the apple have in common, which is not a normal thought process for average people, which is why Newton was able to come up with it. His idea was he bet that the apple hanging from the tree, it's eventually going to get so juicy and succulent that its weight is stronger than the little stem that holds it. And when that happens, the stem will break, maybe in the wind or something, and the apple will fall to the ground. Well, he wondered, he knew his first law of motion and Galileo's law of inertia, which are the same thing. And therefore, he realized if the moon is going in a circle around the Earth, then it has to have some force pulling it towards the center. And he said, I wonder what would happen, or specifically, I wonder if that force is the same force that's pulling the apple down to the ground. And he knew basically what we know now as specifically that free fall results in an acceleration of 32.2 feet per second, which is about 9.8 meters per second. So he wondered, hey, if the acceleration due to gravity at one Earth radius, meaning your distance of one Earth radius from the center of the Earth, if that acceleration is 9.8, then what would be the acceleration out at the distance the moon is away? Well, he knew the moon was in fact 60 Earth radii from the center of the Earth. So that's how far the orbit is. And if you ever try to draw a scale model of the moon and the Earth, you'd probably make the Earth on the order of an inch, and then you'd make this on the order of a quarter inch, the moon, and you'd want them to be about 5.5 feet apart. So that's what kind of scale it is. Now, he had also written a couple 100,000 words in optics, and in that optical study, he discovered that light and sound, for that matter, though I don't know that he discovered that, but light and sound both fall off. Their intensity lessens like 1 over r squared. So if you're 1 meter from the source of light and it's a certain brightness, if you go from 1 meter to 2 meters, then the brightness goes down not by a factor of 2, but by a factor of 2 squared. If you go to 3 meters, it goes down not by a factor of 3, but by a factor of 3 squared, or 9. If you go to 4 meters, it'd be 16. If you go to 5 meters, it'd be 25. 6 meters would be 36. So he argued, if this force that's pulling the apple to the ground is the same as the force that's pulling the moon to the center, then he expected that the acceleration due to gravity might obey a 1 over r squared law. So he said acceleration at the center of the moon, so I'll say moon center. Okay, that's a symbol that we often use for center. The acceleration of the moon at the center should be, since the Earth's radius is the measuring unit that we're using, then the distance from the center of the Earth to the surface of the Earth is 1 Earth radii, whereas the distance from the center of the Earth to the center of the moon is 60 Earth radii, and therefore you should be decreasing the acceleration from 9.8 to something smaller than 9.8, and that would be 9.8 divided by 60 squared. So I'll put a question mark over it because this is what he was wondering. And he took 9.80 meters per second every second and divided it by 60 squared. I'll actually write it that way, which equals 9.80 meters per second over 3,600. Now, when you compute that, you'll get point zero zero. I think it's 278, but let's check it out real quick. 9.8 divided by 3,600 gives me 0.00272 meters per second. So if he finds the acceleration necessary for the moon to keep that circular orbit is that value, then he can be fairly confident that the force that pulls the center, that pulls the moon to the Earth, is the same as the force that pulls the apple to the Earth. Well, what is that acceleration? Well, a moon is equal to, we just learned, v squared over r. Well, what is v and what is r? Well, v is the velocity that the Earth has, and we know that's going to be 2 pi r over the period, and then all that's going to be divided by r as well. So we actually have the ability to calculate this, and I'm trying to look for some numbers real quick just to make it easier. I'm flipping through the book because they put the example, which is kind of weird. They put the example in chapter 5 instead of with this one. Here it is. So the period t of the moon's orbit is about 27.3 days. Now we have to convert that to the proper units. So I'll put it over 1, and then I'll say that 1 day is equal to 24 hours, and that 1 hour is equal to 3,600 seconds. Now you can see that the hour cancels out with the hour, the day cancels out with the day, and we're just left with seconds. And that gives us 27.3 times 24 times 3,600 gives me 2.358 times 10 to the 1, 2, 3, 4, 5, 6, 10 to the 6th seconds. Okay, so that's roughly the period of the Earth's orbit. Uh, excuse me, the period of the moon's orbit. Now I can put these values in, and what we see is we're going to get 4 pi squared r squared over r t squared. Obviously, one of these r's is going to cancel out, leaving that one there. And we can use the fact that the Earth's radius, that the moon's orbital radius is 60 Earth radii, and we know what the radius of the Earth is. In fact, the radius of the Earth is about 384,000 kilometers. So our moon is equal to 60 times the radius, and I should say moon orbit is 60 times the radius of the Earth. And that, of course, is 60 times 3.84 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th meters. So 60 times 3.84 times 10 to the eighth gives me 2.304 times 10 to the 10th, and that's in meters. So now what we have is the R that we need, and we have the T that we need, so we can put all that in. So finally, the acceleration of the moon is equal to 4 times pi squared times 2.304 times 10 to the 10th meters divided by t squared, which is 2.358 times 10 to the 6 seconds. And that has to be squared. So we get 4 times 3.14159 times 2.304 times 10 to the 10th. And that gives me the numerators equal to 2.8952 times 10 to the 11th meters divided by 2.358 times 10 to the 6 meters. And we definitely got something funny going on here. Oh, that's got to be squared. That's why. Okay, so I'm going to divide this 2.895 times 10 to the 11th by 2.358 times 10 to the 6, and then I'm going to square that quantity, and that gives me 0.0027 approximately. So what we found was that the acceleration due to gravity is exactly equal to what Newton expected. And when Newton found this, when he did this calculation, he was the only person on planet Earth that knew exactly why the moon orbited the Earth, why the Earth orbited the sun, why Mercury, Venus, Mars, Jupiter, Saturn all orbit the Earth. And it's because of this force of gravity. So what he conjured was that the force of gravity was 1 over r squared. That's because when he divided by 3600, he got the same acceleration. So the force of gravity is g, a gravitational constant called the gravitational constant of the universe, times m1, m2 over r squared. So what that says is the force is proportional to the product of the masses. So if you double one and triple the other, you increase the force by a factor of 6. And it's also the force is inversely proportional to the distance between them squared. So if you double the distance away, you cut the force down by a factor of 4. If you cut the distance to 1/3 as big as it was, then you increase the force by a factor of 9. That's a big deal. And he also said that the force is attractive and acts along the line connecting, oops, connecting the 2 point particles. So in other words, if you imagine M1 and M2 are points, then if you drew a line from one of those points to the other point, then the force would be parallel to that line, and the force on M2 would pull it towards M1, and the force on M1 would pull it towards M2. So he gave us enough to not only tell us how the force depends on masses and distance, but he also gave us a direction for it. And the value G, after much experimentation, turns out to be 6.67 times 10 to the negative 11th, and that's Newton's meters squared per kilogram squared. That's literally so small that it is a zero followed by a decimal point followed by 10 zeros and then a 667. So it's an extremely small constant, and the force of gravity, therefore, is really, 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 really small. Anybody have any questions on that? All right. Now, that's it. Our time is up. It's 6:50. You folks are free to go. I'll wait for the last person to leave in case anybody has any questions, but you're all free to go.
Thank you. Have a great night.
You too. Thank you. Oops. I just realized I took the actual orbital radius and multiplied it by 60. That's why the figure didn't come out to 0.0027. It should have been 3.84 times 10 to the eighth. So this part is wrong. That's not the right figure. That's not the right figure. This is 3.84 times 10 to the eighth meters, and that is not what we get there. So I'll just correct this on the paper so y'all see it. So 4 times 3.14159. Oh, I also forgot to square the pi, so that's part of the problem. Times 3.84 times 10 to the eighth. That gives me 1.516 times 10 to the 10th meters up top. And then that should give me the 0.0027 in reality. So, Riley or Isaiah, do you have anything to ask or just copying stuff? All right. Well, I'm going to go ahead and call it a day.
Oh,
Oh, you
I
did have
have
a
a
quick.
few questions, Professor.
Yeah, go
Sorry
for it.
about that. So with all the grades that we have so far, I've noticed that we're still missing like a few things, especially for the lab and the grade book. Is there
Yeah.
like an estimate of when we'll get that? That's just solely for my own like
Yeah,
calculation and
that's not on
anxiety.
you. I've just had a lot of things, so I didn't get to do it. I'd planned on having it done by Friday, but we had a small crisis here, so I wasn't able to. But I would say Wednesday I should have the tests returned to you. I've already got the 241 tests graded. I just have to put the grades in, and then lab tests. I'll probably grade two of those tomorrow as a bare minimum. So you'll have two grades on labs, and then I'll start catching up with that. I
Uh,
apologize. That's slack on me. That has nothing to do with you. That's completely me dropping the ball.